Hello, my name is Wasim Gul, and today I will explain classical laminate theory, which is in short known as CLT. CLT. Uh, the main purpose of this laminate theory is to predict the behavior of a laminate. Now let's see how it predicts the behavior of the laminate. Let's have some brief introductions. Classical laminate theory is a commonly used predictive tool which evolved in the 1960s, which makes it possible to analyze the complex coupling effect that may occur in composite laminate. It is able to predict the strains, displacement, and curvatures that develop in a laminate as it is mechanically and thermally loaded. This is a direct extension of the classical plate theory. While derivation of classical laminate theory, we have some assumption like that a laminate consists of perfectly bonded layer. Each lamina is considered to be homogeneous. Each lamina in a state of plane stresses. Each ply obey Hooke's law and displacement are small compared with the ply thickness. So first we need to define some terminology, some input that is required for composite laminate theory. Such input, first we need to define the static sequence. What is the laminate? In this slide, this is the lamina. This is the lamina. What's it's the definition? It is a laminate is an organized stack of unidirectional composite ply, unidirectional plies, unidirectional meaning that the plies have a single fiber direction rather than a wave pattern. The stack is defined by the fiber direction of each ply like this. We see some plies are 0 degree, 90 degree. So um, the fiber angles are measured from a general coordinate system defined here. We this fiber angle, this one axis is the fiber direction, and the two is the normal to the fiber direction, and similarly three will be the normal to this area, normal to the ply, that will be the z-axis. While the whole laminate is defined according to the X, Y, Z coordinate system, which is also known as the global coordinate system, and 1, 2, and 3, this is the on-axis coordinate system, and X, Y, Z will be the off-axis system. This on-axis and off-axis coordinate system, these both terms will be, you will hear from me repeatedly in the next slides. So next, we need to define the material properties. In addition to the stacking sequence of the laminate, the material properties of the composite material must be defined. These composite properties are mechanical elasticity and environmental elasticity. Mechanical elasticity, we have the Young modulus in 1 to 1 and shear modulus, and the Poisson ratio, and the thermal coefficient alpha 1 1 and alpha 2 2. As concerned about the E1, E2, and G1, G2, these modulus and the Young Poisson ratio can be determined directly from the mechanical testing or using the micromechanics theory. Uh, other next finally other the last parameter which we need to define is the boundary conditions, the constraints, the applied loading. Here we have the two types of the loading. The one is the mechanical load, other is the environmental load. The mechanical load, we have the six component. Three is the normal forces in X, Y, and one is the shear friction, and three is similarly we have three bending moments, and the one. So we have the six mechanical loads, and the one is the environmental load that is due to the variation in temperature, which is known as a thermal load. So now first in so before going further going further deeply into the classical laminate theory, first we need to understand the ABD metric. This is very important and well known terminology. ABD metric. What is the ABD matrix? Here you see this is the ABD in this slide. This is the ABD metric. This is essentially a 6 by 6 metric that serve as a connection between The connection is between this applied load and the resultant strain and the in plane resultant in plane strain and the curvature due to this applied load. So now in the next slide we will study how we can get this ABD matrix and how we can get ultimately this in plane strain and curvature. Then we will determine finally the mechanical stress and mechanical strains. So first we need to determine the QIJ, that is a reduced stiffness matrix for each material used in the laminate. If a laminate uses only one time so the composite material, there will be only one stiffness matrix. The stiffness matrix describes uh, the elastic behavior of the ply in plane loading, and this is the formula for reduced stiffness matrix. And these all the terms Q1 and Q12 can be determined using these formulas. So this stiffness is on axis stiffness. So we need to determine the off-axis stiffness. That we can determine the off-axis using this relationship. Here we use the transformation matrix. Uh, this T is the transformation matrix to transfer from the principal direction. Principal direction means the on-axis direction to the global XYZ coordinate system, and to transfer this on-axis stiffness to global axis stiffness, we need these transformation metrics. Next, uh, next thing is that we need to determine the ABD matrices using the following equation. Uh, uh, so first we should see what are meant by ABD physically, what these quantities are. A, this is the A, which is the in-plane rigidity, and the B is the coupling term of the in-plane and the bending moment. I mean, there is coupling between the bending moment and in-plane, and B, it is the uh, rigidity, bending rigidity. So here the Z is the coordinate system, which start from the bottom of the fly and move upward. And we have ZK and ZK1. ZK is the lower surface of the fly, and the ZK1 is the top surface of the glide. So for each glide, we have the two coordinates ZK and ZK1. So we will uh, determine the ABD, ABDC, ABD matrices for each ply. Then we will assemble it. Then we will determine the inverse of ABD matrix, and by using this formulation, we will determine in-plane strain and in-plane curvature. And by using the coordinate system, we can determine the off-axis strain. And once we have our off-axis strain, we can easily determine by using this formula off-axis stresses. So now the question is that we want to determine the mechanical strain, which is also is the on-axis strain. On-axis strain and on-axis stresses can be determined using the transformation matrix. This is for the strain, and this is similarly for the stress. Here M and N can be M is simply cos theta. Theta is the fiber angle. So, if as we have discussed in these very first slides, we have also other than the mechanical loading, we have also the thermal loading. And if we want to add a thermal loading, then the ABD shape of the ABD matrix will be changed like that. In only the difference is that we have added There's some thermal loading, tensile and the bending loading. Rest of the formula is will remain the same. So, putting it all, once we have determined the on-axis strain, on-axis stresses, now it's time to determine either our designed laminate is safe or not. So we need to have some failure criteria, which will tell us, that uh, our design is safe or not. Uh, because we need to decide whether the structure fail or not. This is a very important and very most important step in the design procedure, that we should have confidence that whatever we are going to design, it is able to sustain the applied load. So in other effect, we will also we can also determine the factor of safety by using the failure criteria. Although there are so many failure criteria, such as the maximum stress criteria, maximum strain criteria, and quadratic failure, and micromechanics as well. But here I will briefly, I will just introduce, just discuss about the quadratic failure criteria. The SIVO, which is the most commonly and generally used for the designing of the composite structure. What this criteria say? This criteria say your structure will be safe if the sum of the all internal forces, the sum of the all internal forces, internal stresses will be the less than the one. If it is the less than the one, then your structure is safe. If it is the greater than one, equal or greater than one, then your design structure um, uh, will be fail, and we need to rethink and redesign the uh, redesign the stacking sequence in order to make your structure pass against the given loading condition. Now we will see how we can use all these theory, how we can convert this theory into a tool to for designing the composite structures. Here I have uh, put all this theory in this Excel form, and so I will not go into very much detail. I will not discuss all the aspects of this tool, but just I just want to emphasize that how the knowledge of CLT is important for designing a composite structure. You see, this is the graph which I have plotted using this CLT tool. We can see the strain. I mean, we can see the strain formation, the epsilon 1, epsilon 2, and epsilon 6. And if we change this, the angle, the fiber, if we change the orientation, so fiber orientation, the strain, the formation of the strain location will be changed. Like if we know at the present we have this types of the uh, light sequence, which is known as quasi isotropic light sequence, most commonly used in the designing of the structure. What and this is the symmetric structure. What will happen with this strain? Value of the strain and the rotation of the strain if we change the applied sequence. Let's say we convert all it to zero, and similarly if we change the loading to only the unit load, and that will act on the. Suddenly we see we only have this is the uniaxial strain, and uniaxial strain, and the shear strain is zero, and the other strain in the transverse direction, into direction, is going to negative. This is quite um, I mean obvious that if you are applying unidirectional strain, so other direction will contract. It will have an active strain, and so similar we can also see here in this graph. I have plotted the failure criteria. This is the all this is the SIBO failure index. If, as I told you, if the your structure will be fail if it, and the sum of the internal stresses will equal or greater than one. So we'll see how it will reorient uh, the failure index if we change the again the ply angles. Let's say 45 minus 45, and I'm going to design 90, and the 90 is 45 minus 45. So here we see thus a symmetric failure index we can get, and the we can get, and we also see that no the formation of the strain and the orientation of the strain is also changed. So by using, in short, this is the very important tool. By using this tool, we can predict the properties of the composite structure that is, um, um, and that that uh, by using this theory we can also design the pressure vessel, the hydroplanes, and the many difficult structure by using just simple theory. Thank you for watching.